SIP9 Hub. Hi there. Welcome to another episode of SIP9 Hub. This is the first episode of our new series which talks about the basic inferential tests. This presentation talks about the most important elements and it provides us the process of doing hypothesis testing. Let us start by defining first what do we mean by a hypothesis. But before we continue, do not forget to like this video, hit the subscription and notification bell to stay updated of future videos. In the world of research and in the world of statistics in general, when we say hypothesis, we are referring to a statement about one or more population. Take note that the hypothesis is talking about the population and not the sample. For example, this is the population, and in your research, you want to talk about this population. However, for some reason, you are only able to gather data from a sample. Either this is the practical way of generating information, or this is the only possible way of gathering your data. It's through a sample and not a population, so that the information that you only have is the information coming from a sample. And since your objective is to talk about the population, it is not always correct to directly use that information you gathered from the sample to conclude about that population. This is the very reason why we do a hypothesis test. We are actually testing the information that we gathered from a sample because your objective in your research is to talk about the population. When you gathered your data from the entire population, you did not only take a sample, but you performed total enumeration. That is the term we use to mean that your data comes from a population. Then hypothesis testing will be meaningless because you are talking about the population and you already have that information that talks about the population. So that if that's the case, then we do not do hypothesis testing. Also, we are not testing the information we gathered from a sample to conclude only about the sample. So let me reiterate to you that hypothesis testing is all about concluding about the population because the information that you have, the data that you gathered, is only coming from a sample. This is the reason why we also call it an inferential test, because we are actually inferring from a smaller portion of your population to talk about the population. These are the first elements of a hypothesis test. So whenever we do a hypothesis testing, it should be clear to us which is which. What is our null hypothesis and what should be our alternative hypothesis. Let us consider the symbols that we are using here for our null hypothesis. We are using H sub O, or sometimes we simply write HO. For alternative hypothesis, we have H sub A or HA. Let us try to differentiate the two. The null hypothesis, so it's a statement about the population. And this statement serves as the status quo or the statement that we adopt until proven false. If you have encountered a research, the null hypothesis is normally illustrated using the following keywords. So if the research is all about comparison, you would see the keyword no significant difference. The statement including this keyword is our null hypothesis. No significant difference between or among quantities is synonymous to saying that these groups that we are comparing are equal. That is, if we are comparing in that particular research. If we are trying to correlate or explore the relationship of variables in a research, the null hypothesis is normally indicated by the keywords there is no correlation. Alternative hypothesis is simply the contradiction of a null hypothesis, and the alternative hypothesis is adopted, it's proven, it's accepted if we are able to prove that the null hypothesis is false. So it's literally our alternative hypothesis. So in our null hypothesis, if we are saying that two quantities, say A and B, have no significant difference, or A is not significantly different from B, in our alternative hypothesis, we say that there is a significant difference between the two quantities. Or it's the same if we say they are equal. Or we say that one quantity is less than or greater than the other. For correlations, if the null hypothesis is a statement saying that there is no correlation, for alternative hypothesis, we contradict this statement and say that there is a correlation. Normally, in a research, we want this result. But mind you that in a research, we are not trying to manipulate the data so that we would reject the null hypothesis and accept the alternative hypothesis. It should be based from our analysis. This is because I have some observation that some researchers, because they want the alternative hypothesis, they biasly change their data. We should not do that. Another element, we need to differentiate parametric test from a non-parametric test. So these are both tests, but they are different in terms of the assumptions that we assume when we do them. We do a parametric test only if the sampling distribution of our data is bell-shaped or normally distributed. This is a bit technical, so let me give you an illustration. Let us read this one. Suppose you have a population, you have identified already your population. Let us take a sample and then compute the mean of that sample. Let us write it down. And then we go back to that population. Let's take another sample different from our first sample. So we have a second sample. From that second sample, let us do the same. Let us compute the mean. Let us do this infinitely many times. So there are a lot of different samples coming from the same population. If we are going to graph the means that we have computed from the different samples, the graph is a perfect bell curve. This is one of the assumptions that should be met before we can use a parametric test. Not only that the sampling distribution is normal, but the data inside each sample. Remember that we took a lot of samples. For each sample, if we're going to graph it, it should be also normally distributed. And then the last assumption, remember that we are talking about the mean already. It's assumed that we are computing the mean. Therefore, our variable must be at least interval. So it could be ratio or interval. Non-parametric tests are alternative tests if we are not able to meet the assumptions for doing a parametric test. For example, the sampling distribution is normal, or we are working on variables that are not numerical. Normally, we are talking about ordinal variables for a non-parametric test. By practice, it's rare to see a researcher that really tests whether the variables are normally distributed before conducting a parametric test. It's like a cultural practice that if it's numerical, we immediately do a parametric test. But the most appropriate way to conduct a test is to really identify whether it is appropriate to use a parametric test or a non-parametric test. For non-parametric test also, we are actually testing the medians because our variables here maybe are ordinal. Some examples of parametric tests, we have the z-test, t-test, f-test, or what we call our analysis of variance, or ANOVA for short. Do not get intimidated with the following test because we will be talking each of them as we move forward. The non-parametric equivalent of this test are sign test. We have sign test, Mann-Whitney-U test. We have our Wilcoxon match pair sign round test, Kruskal-Wallis H test, and we have the Friedman test. Another element of a hypothesis test is called a test statistic, and this is simply a value computed from the data gathered from a sample. Remember, we are doing a hypothesis test because we want to talk about the population, but we only have a data gathered from a sample. The information that we compute from that sample is called a test statistic. Later on, this value that is computed from a sample will be compared to a hypothesized value, so that if it's too different or very similar, then we may say that our conclusion is correct, our null hypothesis is accepted. Otherwise, it is rejected. Depending on the type of hypothesis test being conducted, the test statistic varies. So I have presented to you a while back the different hypothesis tests that we can do. So for each of those tests, there is a corresponding test statistic. For example, for a z-test, the test statistic is a z-score. For t-test, we have a t-score. For f-test, normally this is applicable if we are conducting analysis of variance, we have f-statistic. For non-parametric tests, we have the binomial or z-score for sign test. We have the u-statistic or u-score for Mann-Whitney u-test. We have the capital T score. It's different from the t-score here. For Wilcoxon match pair signed ranks test. We also have H-statistic for Kruskal-Wallis H-test and the chi-square statistic for Friedman rank test. Alright, this is the more technical concept. It's a lot of things, so we are going to discuss them slowly. Let us start with the numbers that we see on our x-axis, the numbers that are here. These numbers are actually where we plot our test statistic, so that the value of our test statistic could be anywhere this axis. So it could be anywhere here. This value here, the middlemost value mu, this can be thought as our hypothesis value from which we are trying to compare the test statistic from. We also need to understand the concept of the acceptance and the rejection or critical region. This white portion here is the acceptance region. This portion here, this green portion at the both sides of our distribution, this area here is called the critical or the rejection region. And where do we use this one? If the test statistic, this value here, lies at our acceptance region, then we conclude that the information that we gathered from that sample, that is our test statistic, since it is lying in our acceptance region, we are saying actually that it is not different or it is not significantly different from that hypothesized value, or we call it the parameter. Now, if the test statistic is located somewhere in our rejection region, so these regions here at the both ends, then we say that the test statistic, the value of the test statistic, is significantly different from that hypothesized value. Now, what is this value here, the green dot on our x-axis? This is called the critical value. The critical value is actually the boundary that separates the acceptance region from that of the rejection region. So that in this particular example, for this particular test, since the test statistic, this statistic here, lies within our rejection region, then we conclude that the test statistic is different or is not equal to the hypothesized value. In terms of our null and alternative hypothesis, it's the alternative hypothesis that is true because the two values here are too far from each other. They are too different. Let us have another example. What if we move the test statistic somewhere here? So it moves to the right. This test statistic moves to the left. That movement, that addition or subtraction of that value of that test statistic is not really enough to still conclude that the test statistic is the same as our hypothesized value. So we still say that the test statistic is different from that hypothesized value. Let us move it further. It's not yet there. It's still located. This value is still located in our rejection region. But if our test statistic is increased, so it is increasing so that it gets here, then we say that the test statistic is not different. Remember, that is our null hypothesis. It's not different from our hypothesized value. So we accept our null hypothesis. Let us move further. Then this is more evidence that the test statistic, that value that we gathered from our sample, is not really different from our parameter or the hypothesized value, the value that we are assuming for the population. So these are cases where we accept the null hypothesis. These are cases where we reject the null hypothesis. Now, what about the red area in the green area that we see here? For each test statistic, there is a corresponding area. So it's area under this curve, but it is bounded by that portion where the test statistic lies. For this example, the red region. This region is called the probability value corresponding to that test statistic. So it is just the area to the left of our test statistic. If we are referring to this test statistic, it's the area or at the right of our test statistics. And these areas are called the probability value corresponding to that test statistic. For our critical value, since this is actually basically the boundary, the critical value is a test statistic that serves as a boundary between the acceptance and the rejection region. The probability value corresponding to our critical value is represented by the green area. And what is the use of our probability value? We presented a while back that we can actually identify whether to reject or to accept the null hypothesis by just basing it on whether test statistic is less than or greater than the critical value. But we can actually do the same by considering the probability values and not only the test statistic. In the ancient times, or before, when the statistical softwares are not that really developed, people actually uses test statistic and this critical value. They manually compute this test statistic and they identify the critical value using a table. I'm going to show you an example of these tables where we can look our corresponding critical value. So for Z test, it is this table. It's a very long table. For T test, this table here. For chi-square distribution or for F test, we have the following table. So that is before, when, although we can still do this one, but this was more prominent when, as I have said, the statistical softwares are not really that developed. But today, there's really a lot of softwares that we can use, and the softwares can easily compute the probability values corresponding to those test statistics. Remember that we have to look for the critical value using the tables that I have presented a while back. But for probability values, this is some sort of fixed by reliable researchers. This is actually our culture. In terms of probability values, the boundary actually is set to be 5%. Maybe we can understand this further if I present to you what really probability values mean. So anyway, for this green area here, statisticians, researchers have set this one as 5%. So if your critical region is found at the both ends of our distribution, they divide 5% into 2 so that the area of the green region here is always 2.5. This is our rejection region. So that the probability value for here, for this green area, is 2.5. This is also 2.5. And why again? Because we are setting that the rejection region, the probability value is equal to 5%. This also means that the probability value for this particular test statistic here is illustrated by this green area here. And because this area lies within our critical region, this green region here, still we conclude that the test statistic is significantly different from the hypothesized value. It is the same here. The area, the red area here, is within the green area, the critical region. So we conclude that this test statistic is different from the hypothesized value. If the test statistic increases, of course, the area, the probability value for that particular test statistic will also increase. So that in this particular example, based from the probability values, the red areas, not based from the test statistic, we can immediately see that we are going to accept the null hypothesis. The null hypothesis says that the two values here, the hypothesized value and the test statistic, are not significantly different. Now, let us proceed to what we really mean by alpha. By the way, alpha corresponds to that probability value that we set for the green area here, the probability value for the critical value. So again, it's set, it's 5%. What does it really mean? Alpha equal to 5%. Alpha is called the level of significance, and of course are normally small, like 0.05 or 0.01 or 0.10. But this is what I want to show. Alpha is the probability of committing a type 1 error. We have a new concept, type 1 error. What do we mean by type 1 error? Let us compare type 1 error from another statistical error. We call it type 2 error. Type 1 error refers to the error that we do when we reject the null hypothesis when it is actually true. Some call this error as false positive. Type 1 error is caused by random chance. For example, sample is not really representative of the reality, or it could be caused by improper research technique. Whereas type 2 error is an error that happens when we accept the null hypothesis when it is actually false. Let us provide an example so that we can better understand this concept. Anyway, it's called false negative type 2 error. Suppose we have a null hypothesis here about COVID-19 and we are referring to a person. The null hypothesis is you are not COVID-19 positive. If that is our null hypothesis, type 1 error happens when a person tests positive when he does not actually carry the COVID-19 virus. We are saying that that person is positive, but in reality, that patient does not have that COVID-19 virus. So maybe the symptoms are just really similar to that symptoms of having the COVID-19 virus. That's why we call it false positive. It's positive based from the result of the test, but in reality, it's false. That error, this error that happened is called a type 1 error. If we reject this one, we say that you are COVID-19 positive. That is also the same as rejecting the statement that you are not COVID-19 positive. But in reality, that person does not have that virus. Type 2 error happens when we conclude that a person carrying the COVID-19 virus tests negative. This is the reason why we call it false negative, because we are accepting the null hypothesis. You are not COVID-19 positive means that you are negative. So we are saying that that person is negative from COVID-19 virus, but in reality, that person carries the virus. So maybe the technician swap, so it's an error, swap the specimens, or some other reasons, or just caused by a random chance. Another example, here is our null hypothesis. The new COVID-19 virus vaccine, we are referring to the vaccine, is not effective. So this is the heart of the sentence, that vaccine is not effective. Type 1 error happens when we reject that the vaccine is not effective and say that it is effective when in fact it is not actually effective. and the clinical trial results made as basis for saying that it is effective are purely coincidental. So it's an error. That error is called a type 1 error. So since it's an error, we are trying to avoid this one. Type 2 error happens when we accept that the vaccine is not effective. We are accepting the null hypothesis. However, in reality, the vaccine is truly effective. Maybe those people who belong to that clinical trial group are either very unique or very weak, such that even if the vaccine is really effective, it was not effective on them. Now, I have a question for you, for our listeners. Between the two types of error, type 1 and type 2 error, which of the two types of error is more forgivable? Because they are different, but they are both errors. Kindly tell your answers by typing it in our comment section down below. Okay, let's go back to our discussion. Type 2 error is not really covered in this presentation. Type 1 error, that is what alpha is measuring, that's the level of significance. And this is the reason why, if we go back to the previous slide, alpha are small numbers. It has to be small because again, these are errors. And if we are doing a hypothesis test, we want that error to be really small. So those statisticians or researchers who said that the acceptable alpha or the allowable alpha, the allowable type 1 error that we can forgive is only 5% or 0.05. So a test with 5% level of significance means that the result of the test, there is still a 5% chance that you are wrong. If you want to make your alpha this small, it's 0.01 or 1%, that is even better. That's why we hear the term significant and highly significant. Significant if we reject the null hypothesis at 5% level of significance, meaning our boundary, our critical region is at 5%. The area is equal to 5. If we set our alpha equal to 1%, then we are actually constricting our test, hypothesis test, to having a chance of being wrong just at 1%. So of course, there are implications if we use 5% as our level of significance and if we use level of significance equal to 1. It is more difficult to reject the null hypothesis if our alpha is only 1%. This is really rare. Alpha equal to 0.10 or 10%. It's really difficult to see from those published journals, researches that we see around. But anyway, you can do that. This only means that you are increasing the chance of committing a type 1 error. For the type 2 error, as I mentioned a while back, it is covered in another lesson that we may not present soon, but it exists. FYI, if alpha measures the type 1 error, the chance that type 1 error occurs, beta, the Greek letter beta, represents the chance of committing a type 2 error. Let us proceed. Difference between two-tailed test and one-tailed test. So let us go back to this figure. In the previous slides, we've seen that the critical region are found at the both ends of our distribution. That is because our test statistic is said to be significantly different from that hypothesized value if it is too low, too far from that hypothesized value. So meaning it could be very low or very high. So that the critical region is found here and here. Because of that, we are dividing alpha into 2. This may be because it is not specified in our null hypothesis that we are testing whether one quantity is greater than or less than another one. We just generally indicated there that the two quantities are not equal. So it's either A is less than B or A is greater than B. That is the reason why we do this. If we specify that we are only testing for cases like A is greater than B or A is less than B, then we can only concentrate at one end of our distribution. So for example, in this particular case, this test is corresponding to a null set stating that the test statistic here is significantly greater than the hypothesized value. This is what we are trying to test. Or we are testing whether the test statistic is significantly lower than the hypothesized value. These are considered one-tailed tests. And how do we know when to conduct a two-tailed test or a one-tailed test? It should be indicated in the problem. So do a hypothesis test whether two quantities are significantly different. If that's a statement, then we are doing a two-tailed test. But if it is specified in the problem that we want to test specifically whether A is greater than B or is less than B, then we should conduct a one-tailed test. Here is the summary of hypothesis testing. Of everything that we mentioned, the first thing to do is to identify your null and alternative hypothesis. And then, you identify also your test statistic, your appropriate test statistic, because there are a lot of tests, and for each test, there is a corresponding test statistic. This test statistic, once identified, that's what we compute in step number 4. If we are doing a manual computation, the critical region, we have explained this one. If we are identifying the critical value, we use a table. But if we are using the probability values as our reference to say whether we reject or accept the null hypothesis, then we actually use the probability values from which the critical region is set to be either 5% or 1%. And then we decide. We decide whether to reject or accept. So if the test statistic is within the acceptance region, then we accept. If it's within the rejection region, then we reject the null hypothesis. That ends our presentation on hypothesis testing. Thank you for listening. For our next presentation, we will be talking about the different basic inferential tests that we normally use in the social sciences. Kindly click on the link above to proceed to that video.